Hello and welcome to our webinar today. Our topic for today will be looking at return on investment analysis with Fronius Inverters. And doing this webinar today is myself, David Mwangi. I'm the Technical Sales Advisor for the Eastern African region. I'm based in Nairobi, Kenya. And joining me also is Bailon Kwatse, the Technical Sales Advisor for the Southern African region. He's based in Joburg, South Africa. Our agenda for today will be just a few topics. We look at understanding ROI or return on investment. We will also dwell into CAPEX, OPEX, look at the yield of the system, monitoring as well as analysis, and then finally give you a system example based on all those factors that are affecting the return on investment. As usual, before we start, if you have any questions, please feel free to post them in the questions area, and we will do our best to answer these questions as we go along. In addition to that, at the end of the webinar, please feel free to give us your opinion. Tell us if you have liked this webinar, any topics that you'd like to be covered in the future. We always appreciate your feedback. So let's get started and start with return on investment. But the first thing to do is to understand what we really want to dwell into as far as the return on investment is concerned. And this is referring to recouping the associated costs of an investment over a sorry about the lost connection. I've seen a few guys have expressed the same concern. So let's start again. So I hope now you can hear me. I was just explaining the concept of the ROI, which we want to address in today's webinar. And this basically referring to recouping the associated costs of an investment that is expressed over a period of years. And the ROI can also be argued as the project's break-even point. So these costs would include, of course, the initial expenses, which we refer to as the capital expenditure of the project, as well as the operating expenses. In terms of a simple formula to work out what the ROI or the return on investment of the system is, this would be expressed as the sum of the CAPEX, which are the capital expenditure, as well as the operating expenses. So you add those two together, and this would give you what is the generated revenue of this particular project. So if you look at the generated revenues over a period of time, or the savings that you have realized, divided by the CAPEX plus the OPEX, that gives you the return on investment. For us now to understand what is the mix of the CAPEX as well as the OPEX, I would like to break down a bit these two cost aspects. So if you look at the CAPEX of a PV system, you would realize that you have several sections of it. So this pie chart, for example, shows us the various costs that are associated with the CAPEX or the capital expenditure. So we have the module cost, which you can see here is the biggest proportion at about 44% of the project or the installation. We have the balance of system, which is 33%. And then we have things like labor and the inverter cost, which is only at 9% of the total project cost. So if you look at this inverter cost, is actually quite a small proportion of the entire system cost, but it has a huge influence on the performance as well as the return on investment of this particular project. So the balance of system components are much higher compared to, for example, the inverter at 33%. And the question therefore begs, can the inverter that is being used for a particular project influence the cost as far as the balance of system components are concerned? So If we break down further the balance of system costs, we are going to realize that we also have quite a number of things that we can consider here. So we have the racking system, we have the cable trays, we have the DC and AC distribution boxes or combiner boxes, and we also have the grid connection. So we could say this is things like the transformer, switch gear, and so forth. So these costs, which are the balance of system costs, are not in any way related to the inverter or the solar panels. So these are things that must be procured regardless of the kind of panel array or inverter system you use. The racking system, cable trays, many grade connection not affected by the inverter as well. But the inverter could have a huge impact on the AC and DC cabling, as well as the AC and DC distribution boxes. So with the right design, choosing the right inverter can make huge savings, and therefore, with huge savings on the capex, you can shorten the return on investment period. We have done a few comparisons, for example, between our Snap Inverter Echo and a 60 kilowatt competitor inverter sized for the same kind of AC power. And then we compared both the centralized and decentralized topologies with these two inverters. So the outcome that we will not go into much details to get into is that when it comes to overall capex analysis, to make the best decision on the inverter to use, it's not only enough to consider the cost of the inverter or the device alone. So you have to decide based on the comparison of all incurred cost plus what is your expected yield. So in this comparison of the Fronius Inverter Echo, Snap Inverter Echo 27, and the 60 kilowatt competitor, we looked at a roof-mounted system, which is about 408 kilowatt peak, and this system is situated in Central Europe. So as far as the balance of system components are concerned, with these two inverters, what we realized is that if you look at a central inverter system topology, that is, between the Fronius and the 60 kilowatt competitor configuration, you would realize almost 62% savings on the BOS. So comparing the two systems. And therefore, even with the central design topologies for the two systems, we can see that the Fronius Snap Inverter Echo still gives you quite a bit of advantages as far as this is concerned. And then one interesting aspect regarding the distances, you would realize that the moment you exceed 100 meters going forward, depending on the distance of the PV array to the inverter, then it becomes most cost effective when you use the central design topology, as we can see with this topology as far as the Fronius Snap Inverter Echo is concerned. So therefore, in terms of the summary that we can deduce from that is that the distance from the PV modules to the point of interaction, this is the feeding point, plays an important role as far as the cost on the balance of system components is concerned. This could affect things like the cable cross-section has been used. And in addition to that, this can also relate to whether you have chosen to use a centralized or decentralized topology. So for this comparison, as we have seen for this 408 kilowatt example, there is a 62% clear benefit when it comes to the BOS cost when using the Fronius inverter in comparison. Let's now have a quick look at the OPEX of the system. When it comes to the OPEX, this refers to the operating or the ongoing daily expenses for commercial operations. And OPEX consists both the planned and the unplanned service. And major planned service activities, for example, could include things like modules cleaning, cable connections inspections. It could be cleaning the inverter cooling system, especially when a passive cooled inverter is concerned. It could be things like checking the voltage and current parameters of the PV array to make sure that the PV array is still generating within the designed parameters and so forth. So in terms of the OPEX analysis, so we have here also a comparison between an actively cooled Fronius inverter Eco and a passively cooled competitor inverter. So with a passively cooled inverter, you would require normally more cleaning to make sure that you do not get yield losses from accumulation of dust on the cooling fins, because the effect on the accumulation of dust, it means that the inverter is not able to cool itself sufficiently and therefore automatically derates the power output. Another important aspect as far as the OPEX is concerned, should something go wrong with, for example, a Fronius snap inverter, you are able to replace a board as opposed to replacing an entire inverter. And therefore, even in terms of the number of people you need to consider to site, with a Fronius snap inverter, for board replacement, you can only send one person to site. And therefore, even in terms of the personnel costs for OPEX, then these are a lot lower. For larger commercial inverters, you would at least need to set 2 people. So a crane probably, if you need to replace the inverter, would be required. And therefore, more manpower would be equal to higher costs. So when you talk about bigger commercial inverters, we, for example, do have also the Fronius Tauro 100. So this inverter for installation purposes, you would require maybe 2 to 3 people. But also the service concept allows that only one person is sent to site for replacing something like a power stack. So you do not need to send more than one person to site, even for the Fronius Tauro commercial inverter. So what this means in a nutshell, if you look at the OPEX analysis as far as the service aspect is concerned, for a passively cooled inverter in comparison to the Fronius Eco 27, which is actively cooled, you look at what is the number of times for scheduled maintenance that you need to go there, and then the service callouts. So we are going to consider the number of site visits per year, the number of people that you need to set there, what is the duration for this service trip, what is the workload per year, the hourly costs, and then what is the total labor cost or service cost for 1 year. So if you look at the passively cooled inverter, we would have at least 2 service scheduled maintenance service visits per year, at least 1 service call out. And then for scheduled maintenance, maybe you said 1 person to site for the passively cooled inverter, and at least 2 people for if something goes wrong with the inverter and you need to replace it. For the Fronius Eco 27, for both scheduled maintenance and the service callouts, you would need to set just 1 person. And the big difference here is that you just need at least 1 scheduled maintenance per year. And this would mean, in terms of the workload, for the Fronius inverter, you would realize a scheduled maintenance workload of about 10 hours per year. And for the passively cooled inverter, you're looking at a minimum of 20 hours, because then you have at least 2 people going there for 10 hours. And if your hourly costs, this could vary depending on where you're operating from. So if your hourly costs, for example, are 60 euros per hour, then you can see that for 1 year, to set for the passively cooled inverter, you need to spend about 1,200 euros. And for the service callouts, about 600 euros. For the Fronius Eco 27, you will spend about 600 euros for the scheduled maintenance and about 120 for the service callout. So you have a difference, quite a big difference between the total of the 2 systems. And therefore, this is a huge impact that you would have for the Fronius Eco compared to the passively cooled inverter. So the more you pile up onto the OPEX as far as the schedule maintenance and service callouts are concerned, the longer your return on investment period becomes. So let's now look at yield, how you can go about analyzing the yield of a PV system. So when you talk about the OPEX and the CAPEX of the system, these are not enough to determine the cost effectiveness of a system. So the expected energy yield should strongly inform the inverter that you're going to use for that particular system. For example, two important factors that would affect the choice of inverter to use is, for example, what is the impact of yield due to the ambient operating temperatures? And then the second question would be, what is the impact on yield due to things like shedding? So for the expected or the actual energy yield, this is what you have to use to determine the ROI or the levelized cost of energy. So if you want to calculate the levelized cost of energy, this would be given by the sum of the initial expenses, which is the capex, plus the operating expenses, divided by the energy yield in kilowatt hours over a given period of time. And this would give you unit cost in whichever currency per kilowatt hour. And this would be your levelized cost of energy for this particular installation. So when it comes to temperature, how do Fronius inverters deal with ambient temperatures? So what we do know is that temperature has a negative effect on production. So if an inverter is therefore exposed to high temperatures, the output would be reduced. This, of course, would have a negative impact on yield. And this, in addition, means that you would extend your return on investment period. So if the inverter then is actively cooled, you have a better derating behavior because there is a stronger cooling effect than a passively cooled inverter that easily goes into derating mode to avoid damaging the electronics. So on this graph to the left here, we are comparing two inverters, one from Fronius operating at both 580 volts on the DC side and at 850 volts. And then a competitor inverter operating at 500 volts and at 800 volts. So what we can see is that at 580 volts, which is actually a nice MPP voltage, the Fronius inverter is able to give you maximum output up to about 45 degrees Celsius ambient temperature. And the passively cooled inverter starts derating just at above 30 degrees Celsius. So if you are to look at the difference between these two derating points, comparing the Fronius and the competitor, this would tell you how much yield you're going to lose on if you're using a passively cooled inverter in this kind of ambient temperatures. So to understand the effect this has on the yield, we look at this particular graph. So this is for a system that is about 99.84 kilowatt peak, gives out 90 kilowatt AC power. And this is an installation in Australia with an annual yield of about 647 kilowatt hours. So you can see that when you have the possibility for maximum output, so this is the production curve, as we can see it with active cooling. This is also the point when the ambient temperature would be at the highest. So we are looking at the possibility of the module temperatures approaching even above 50 degrees. So if you are to use a passively cooled inverter, when then the ambient temperature would be at the highest point, then the passively cooled inverter automatically would derate the power output. And therefore, if this setup was done with a passively cooled inverter, the yield losses in this case would be significant at about 15%, which would be about 96 kilowatt hours for this particular system. When it comes to shedding, this is also another important factor to consider for inverter choice, how the inverter behaves if the system is shaded. We have an example here for a partial shading of a PV system in the morning hours from about 8:45 to 10 a.m. And the daily production curve without an integrated solution against shading would be missing quite a bit of power in the morning hours, as you can see here from 8:45 all the way until 10. So, but Fronius has a solution for this as well. For all Fronius inverters, they have a shading mitigation solution integrated. And this is what we refer to as the dynamic peak. So the dynamic peak manager finds the optimal operating point, even in the case of shading, and therefore it gives you more flexibility and more yield for this particular installation. So in most cases, when you have an inverter without the dynamic peak management to mitigate against shading, when you have partial shading, for example, if you look at these two graphs at 9 a.m. and at 8 a.m., you have two possible maximum power points. So we have what we refer to as the local maximum power point, and we have what we refer to as the global maximum power point. So if the inverter does not have the dynamic peak management, it gets stuck at the local maximum power point, because any shift of the operating voltage downwards or upwards realizes that the actual power output is reducing and therefore gets stuck at this point. But the Fronius inverter using the dynamic peak manager would sort of scan this IV curve every several minutes, 5 to 10 minutes, and therefore is able to find always a better global maximum power point, even in the case of shading. And therefore, as a result of this, we can realize 7% more yield with the dynamic peak manager. So if you put together the two aspects of the active cooling, then the shade mitigation algorithm, which is the dynamic peak manager with the Fronius inverters, you can see that you have significantly more yield with the Fronius inverter design compared to competitor inverters. And therefore, the more yield you are able to get out of the system, the higher you are, or the faster your return on investment for this particular system. And at this time, I would like to hand over to my colleague Byron to be able to take on the next session. So Byron, please.
Thanks, David. So next up, I'm from Fronius Inverters. So you get integrated monitoring, which is hardware which is already integrated into the inverters themselves. You will require a smart meter in the system when wanting to do or making use of the integrated monitoring. It's software which is free of charge. So this is referring to our Solar Web, which is our online portal, as well as making use of tablets that you're using for your systems. The system monitoring, it allows for easy management of multiple systems. It allows for switching between widgets and list views. It's designed to make it a lot easier to view and analyze which sites you wanted to switch between, for example. It also allows for easy error messaging. So you will receive a simple email, basically referring to the total system uptime, will allow you to then do production and comparison in that regard. The data analysis. The system extension when making use of analysis. So from the customer's perspective, important questions by the customers themselves. So what's the PV yield and own consumption rate of last year? How high was energy cost savings per year, for example? And then also how to improve consumption and self-sufficiency rates. What are my savings if using a Fronius Ohmpilot or battery storage in the system? So how can you as the customer benefit, for example? So the energy balance is what you'll have to do is you'll go to energy balance when you're on solar.
Okay, sorry. It seems like Byron is having some issues with the connection. So I would like to take over and continue with the remaining part of it. So, but I think I would like to start a few steps back at the data analysis. So in terms of the data analysis that you can do right from SolarWeb, and this is for customer care. So this starts with the registration of the PV system. It goes on to the data monitoring once the system is up and running in SolarWeb. And then you go into the data analysis. So once you have accumulated data over a certain period of time, then you go into data analysis. And then lastly, you also do system extension possibilities. So you check what are the options to extend the system based on the analysis that you have done. So from the customer's perspective, there are some important questions that the customer can ask, and this can form a discussion point between you and the customer. And this could be, for example, what is the PV yield and my own consumption rate over the last year? How high was my energy cost savings over the last year? How can I improve as a customer my own consumption as well as the self-sufficiency rate? And also, what would be the customer's savings if, for example, they were to integrate something like a Fronius Ohmpilot or a battery storage system? So when it comes to answering these questions, you have to go back to SolarWeb and conduct your analysis there. And one of the things that you'd have to look at is the energy balance of the system. So the energy balance of the system is actually like the one of the important dashboards within the monitoring platform SolarWeb. And once you click on that, you're going to go directly into the production curves. So the production curves would be able to show you switch between production and consumption, and it would tell you how much you are consuming directly. So you can see this in yellow. So this is what the PV system has generated, for example, for this particular day. And it will also show you, if you have a smart meter, what is the overall consumption for a 24-hour period. You can also check directly the consumption. Are you taking mostly power from the PV system, or are you also taking power from the grid? And this assists you to answer to the question, what is the self-sufficiency level and how can it be improved by the customer? So in this particular case, for example, we can see that for these 3 months, March, April, and May, the customer has greatly benefited from the PV system, because we can see this meeting over 50% of the energy requirements for every month. So therefore, the self-sufficiency level is able to be worked out by SolarWeb directly. And this looks at how much you're taking from the grid, how much you have consumed directly, and therefore it gives you a total of your consumption for that particular month. For example, for this year 2024, this customer in March 2024 was able to have a self-sufficiency of about 59%. And therefore, you can answer very easily when you're doing your energy analysis and energy balance, checking what are the figures in SolarWeb, and you can advise your customer how then to improve these figures. So in terms of the return on investment, you can also check quickly from SolarWeb, and this is why it is important when you're commissioning the system, you enter the actual cost of energy for your particular region. So there's always the section where you enter the cost of electricity per kilowatt hour. And these are the figures that eventually then SolarWeb uses after it has accumulated data to be able to work out for you what are your savings on a daily basis, on a monthly basis, or an annual basis. So for example, we can see that in April 2024, this particular customer was able to save on April 5th about $508 US dollars. And therefore, you can also see cumulatively for the entire month or for an entire year. And this also assists you to tell the customer, because you're saving so much over a period of 1 year or 2 years with the initial cost of the system, then we are looking at X amount of years for you to be able to recover the initial investment in this package or in this kind of PV system. And therefore, that's why it's very, very important to always bring your systems to SolarWeb, preferably for grid connected systems with a smart meter, because then a smart meter is able to tell you what is the overall consumption and gives this data to SolarWeb. Then SolarWeb is able to work out this kind of detailed data for you. Another important aspect based on the data that is available in SolarWeb that you can also consider is the optimization aspect of the PV system. And when it comes to the optimization, you can do quite a number of simulations in SolarWeb. So you basically go to the analysis section of SolarWeb, and once you click on that, it can take you to the next page where you can simulate for heating using the PV system, and therefore this is where you can use something like an Ohmpilot for managing the excess energy that is available. We know, for example, in most African countries, we are not allowed to send PV power to the grid, and therefore, depending on the load consumption levels, you have to throttle down the power output of the inverter. So instead of throttling down the power of the inverter, you can simulate for something like an Ohmpilot, especially for residential systems, to be able to use all the excess energy that is potentially on the roof to heat or generate hot water for you. Something else that you can also do is to check, would it make sense to integrate a battery system? So under the simulation section still, you can simulate for a battery storage system. And therefore, once you click on simulate on this particular system, it will show you what is the possible battery storage capacity that you can use for this particular installation. So this kind of optimization analysis would also be a good upselling opportunity for you as an installer, because it allows you to do more business. But on the other side, the biggest benefit to the end customer is that you allow them to become more self-sufficient, and you also increase their self or own consumption levels of this PV system. So having said all that, I would like to show you a system example that brings all these aspects together. And this is based on a food retailer by the name Pichler. And the specifics about this customer is that this is a family-owned company that was started in 2007, and they are in the business of selling organic fruits and vegetables. So their storage facility is about 1,300 meters squares, and they have a cold storage facility or space of about 650 meters square. Parking stations, offices, and halls account for 300 meters square, and they have an EV fleet as well as modern packaging or packing machines. The specifics about the PV system that was installed, that this system is located in Austria with a size of just about 100 kilowatt. Rooftop installation, as we can see on this photo to the right. And it was commissioned in July 2018 with an annual yield of approximately 100,000 kilowatt hours. So the self-consumption rate is about 80%, and the degree of self-sufficiency from this system is 40%. In terms of how much CO2 they are saving from the environment, it's about 53 tons annually. Looking at the energy profile or the load profile of this particular customer, they are in constant operation, like throughout day and night, because of the especially the cold storages as well. And therefore, here you can see the distribution over a period of 1 month, how the energy profile or the load profile looks like. So from this summary and from the initial investment that was done, the installation of the Fronius-based system is able to save for the customer about 10,000 euros per year. And that would indicate, based on the investment of the system, an amortization period of about 5 to 6 years. So this is the return on investment of this particular system, which I would think is quite good, because if you consider the lifespan of a PV system being something like 25 or 30 years, and you're able to recover your investment in 5 to 6 years, then that's a very good, let's say, investment. In terms of the self-sufficiency, this is 40% with a non-consumption rate of about 80%. This customer still is taking 60% from the grid, and therefore, based on this kind of data that you have analyzed, even for your own customers, you can specifically tell the customer that if you did 1 or 2 A or B measures for this particular system, maybe integrate battery storage system, maybe integrate hot water generation by the Ohmpilot, or if the customer is thinking about adding an electric vehicle, integrate the Fronius Ohmpilot to be able to recharge this electric vehicle either using excess energy or even from the battery storage at night and recharging only to the required extent of the EV battery. So in a nutshell, I think you have to think about, yes, you have done the installation, you had some theoretical expectations as far as the savings and the energy generation of the PV system is concerned, but you have to proactively do data analysis in Fronius SolarWeb to be able to advise your customers on a frequent basis, or maybe every 6 months or every 12 months, depending on what you feel is convenient for you, and be able to tell them, yes, we are on track because we can see these are our savings, or maybe we need to do more interventions so that our expected return on investment as we had calculated when we are doing the installation stays achievable. So with that, I think we've come to the end of the webinar for today. For more information, please visit our website. You can go to the download section. For all the webinars that we have done, you can visit the African playlist in YouTube. So there you have quite a number of topics that you can look at. If you'd like to contact any of us, additional details, we are happy to interact with you. If you have any questions for West Africa, please get in touch with Cyprian. For South Africa, Byron, and for East Africa, you would have to contact myself, David. And with that, I would like to thank you for taking your time to join us today for this webinar. We hope that you have gotten a lot of useful insights on how to maintain, operate, and do analysis of your PV systems to make sure that what you promised your customer at the beginning is still something that can be achieved after maybe 5, 6, or depending on the kind of return on investment periods that you have calculated. So thank you so much and have a good day ahead. Bye for now.